Okay, so A2C is a pretty powerful algorithm and it's pretty good. However, as we've seen before, once we include bootstrapping learning, TD learning, with approximation, value approximation or action approximation, we've seen that this might lead to, in many cases, it might lead to instability in learning and even divergence in learning. And this issue is what they try to address with the paper titled Asynchronous Methods for Deep Reinforcement Learning. So specifically, they try to address the issue where the sequence of observed data encountered by online agents, such as the A2C agent, is non-stationary. I mean, the observed states evolve, the distribution of observed states evolve over time as your policy changes, the policy changes. And the online, also there's an issue where the online updates are strongly correlated, right? Which might be an issue for training deep neural networks. We discussed this before when we discussed Q learning with deep neural networks, and we also discussed ways to address or to decorrelate the samples, right? We saw the replay memory buffer, experience replay memory that helped us to break correlations between the samples. However, the issue with the experience replay buffer is that it requires off-policy learning, right? Such as relevant in DQN, because it looks at the past samples. So it requires us to have an off-policy learning algorithm that can be updated from data generated by older policy. And also we saw that once we introduce or we use replay memory buffers, they usually increase the computational complexity or computational requirement because they use a lot of past transitions to do one step in the real world. For each one step in the real world, we sample many previous transitions, a full mini batch of previous transitions. So in practice, we want a deep reinforcement learning mechanism that can decorrelate updates, but in an online manner, and can work with on-policy algorithms, right, for on-policy learning. That is, we would like decorrelated samples from the same policy, if possible. And also we would like it to be more memory and computationally efficient, of course. So in order to do that, they introduced asynchronized updates, where we asynchronously execute multiple agents in parallel, similar agents, and they all work on multiple instances of the same environment, or underlying environment. So this kind of requires us to have a simulation environment. Maybe in the real world it might be an issue to instantiate several similar workers in the same environment, but in simulation it's usually easier, or it is easier. At any given time step, the parallel agents will be experiencing a variety of different states, which can be viewed as decorrelated samples, same workers in the same environment, and each one of them will just go maybe in different directions, and so we have several samples that are decorrelated in essence, unlike samples that are coming from the same episode for the same agent. Such a process enables, as a process of decorrelating or asynchronous workers, this will enable us a spectrum of on-policy RL algorithms to train deep neural networks, because they will produce us with decorrelated samples. For instance, we can use sour science, the bootstrapping, policy gradient, and so on, or vanilla policy gradient. Moreover, it can allow us efficient utilization of standard multi-core CPUs, where maybe running several instances of the same worker, the same policy, might not be expensive with respect to time, right? It might be expensive with respect to computation, but if you can do it in parallel, then usually it's fine. I mean, it's the computation time that we usually care about. And indeed, this is the idea behind the A3C algorithm, asynchronous advantage actor critique. And the main idea here is that we produce several copies of the same actor and critique, and each one of these copies we run in parallel and asynchronously of each other. We compute the n-step return for each one of our workers, and then we accumulate the gradients with respect to both the actor and the critique for each one of our workers. Then we perform an asynchronous update to the actor and the critique at the higher level, right? At the level that produces all of the workers, using the accumulated thread-specific gradients, right? For each one of the workers. Each one of the workers report back and tells us which, provide us with a gradient for updating the actor and the critique, and we perform this update at the higher level, and then we have new, and we do it in a continual process, so the workers might be updated continually, because each one of the workers will finish the episode at different times. So once it finishes, we update the global actor and critique, and we restart the worker again based on our new actor and critique. So they're kind of the same workers and critique, but they might actually, they do change over time, okay? But, so, right, this is a bit of a hand where I'm saying they are exactly the same. They might not be exactly the same at a specific time step, but the hand wavy claim is that they are sufficiently the same, in some sense. Okay, so, and indeed, A3C, when we do the asynchronous workers, it allows us to speed with respect to time, right? It allows us to gain significant time improvements or computational time, wall clock improvements compared to running A2C on a single thread. So the results here present the training time, the wall clock time comparison. So it's not cumulative thread time, it's just a wall clock over several threads, or multi-core processing. And the training time is presented compared to the DQN algorithm and compared to A3C. And you also have one-step SARSA and also n-step Q-learn. And these results are on the Atari video games, and each one of these results is averaged over 5 runs. You can see the DQN results. Oh, the DQN results are provided for different seeds on a powerful GPU. Actually, these days it's not very powerful. It was a powerful GPU back in 2015. And you can see that the A3C, the asynchronous method, is much more simple efficient, right? I wouldn't say that it performs better, because it might be the case that after more training, the DQN agents would be able to reach the same performance as A3C. But you can see here that the yellow line learns much quicker. And that makes sense, right? By the way, as I said before, it's not necessarily that it performs less updates or less steps in the environment. Most of the benefits in training time is due to the fact that it runs training in parallel, right, in the environment.